So hi everyone. So welcome to our Monday's discussion session. So today's discussion, I'm going to give a brief talk about the unit time, and materials. So before I start our discussion, I want to mention one thing. Since we have finished our project A, so we want you to stop your instance in the Jetstream. If you keep running your instance, the running instance is still consume our allocation resources. And right now we don't have any resource there, so just stop your instance there. And so we can request more resources from the Jetstream side. Okay, print tick node. So right now we decided not to use. I mean, the box is not be our platform. We won't post anything in the box. So I will post this PDF or these slides to the edX resources there. So you just go there and download it. So I will update I will update this note, this PDF to the after I finish this discussion. So yeah, but this discussion, this PDF is very easy, so it won't need to write down something there. We just start our discussion about the knowledge, about the content, course content. So don't worry about that one. So let's go to our discussion. So in this unit time, we talk about the distributed data store. So distributed data store can have any other name. I think there should be the distributed file system. So same thing. So a computer network where information is stored on more than one node. So it seems like this is a sample of distributed data store. So in this system there are thousands of nodes in it, and each node will contain a file or some information there. So there's a very normal case about this distributed data store. So think about Amazon. So we suppose Amazon only contains all this information, like this product information, user information, everything in a single node, in a single machine, a very strong machine. What will happen if this machine crashed? So it means every materials, every information is gone because of that node or that machine is crashed. So it will be terrible for Amazon. So for Amazon, the real thing is that it uses the distributed data store. It just store information on different nodes in this system. But for the customer, so customer only can just access the server and they think they're only one machine. But actually for the server side, there are thousands of machines, thousands of machines there. And these thousands of machines can keep the data consistency and availability. So the next step, we are going to talk about the two important features about the data consistency and data availability. So talk about the data availability. So ensure the data continues to be available at a required level of performance. What's that mean? So in the distributed data store system, we are going to save same data in different nodes. So when the user or client sends the read request, so we are going to send this file to the client for their reading request. So the system is going to make sure the server can supply the real file or real data to the customer, and the customer can finish their reading request or can get some reading materials. So about the data consistency. So we know we are going to the system, so the data would be constant in time and for use to be capable of using and showing them in different ways without changing their structure. So we can give an easy definition about this part. So like in our system, there are hundreds of nodes there, and the system manager is going to read, write there in these thousands of nodes. How to keep the new version. Like, so for example, the system is going to read some file in some nodes, and how to keep the versions, new version problem. Like every time the node is going to read, every time the system is going to read data from these thousands of nodes, and how to extract the new version from it, and show this new version, show this up-to-date version, this up-to-date files or data into customers. So this is a very important part about the data in the distributed system. So there are two basic operations in the distributed data store. Well, so one is the read and one is the write. That's the two very basic operations. So for the read, this graphic can show the very clear understanding about read. So for the server just send the read request to the node, and the node will send these files into the server side. So it means the server is going to read some data from the nodes and send the data into the customer. So there's no question about the read part. But the write operation is more complicated because we have to write something new about the file in the different node or in one node. So here, this graph shows something about the write. So first, the server accepts the write request, and it's just to write something new in the file in some node. But how to handle this new information, new update? So we are going to use version. So version, what does version mean? So here for this left graphic, so this sample machine just contains old version 1.0 file. And once the server just finished the write request, so I mean the node just updates the information, new information in this old file into this old version, then the node will have a new version of file. The version will be 2.0. So this new version is quite different from the old version file. This new version contains new update, and the old version is gone. So we won't keep the old version and new version in a single node. It means just a new version in a single node, in this node here. So there's no conflict about the old version and new version. So there are only new version in this machine, in this node. So there are 4 cases about write and read work. So we are going to balance the write and read work. So first one, so how about write own node? So it means, so for the one single node, it should be okay because there are only one single node. But if you think about hundreds of thousands nodes there, so if we want to write to all nodes in this system, it will be a very heavy writing operations. So it will cost a lot of time and to update the information, because every time when the server accepts the write request, it will connect to every node in this system and update the information. It will cost a lot of time, and it's not a good. It doesn't have a good performance. So, but if we write to few node, we have to say in some cases that it cannot guarantee the data consistency. So we have to discuss this balance write and read work in our next slides. But here we have to think about these 4 cases. So here, so the third case should be read from all nodes. So when we get hundreds of thousands nodes in the system, so if we want to read everything from this system, so we have to connect to every node in the system and read it, and then send the information to the customer. So it will be a heavy read operation there. But if we read from few nodes, seems like there are hundreds of thousands nodes there, but we just read from one node. The server just choose one node and read it and send this information to the customer. So this case, so we cannot guarantee the data consistency. Same thing. So if we for example, if we just choose one node from this hundreds of thousand node, and unluckily that node contains the old version, so there's an issue about version problem. There's an issue about the version part. So the customer only can get the old version and can not get the new version. So we have to think about this balance write and read work. So think about these 4 cases and how can we handle it. So if you watch the videos of this lecture, so you will know there's a protocol developed to help us to manage this work. So the protocol is the quorum protocol. So here, there's a definition, so description. So when a user wants to read a data object and the data object is not replicated across every server's nodes in distributed data storage system, how does the system know which of its servers or nodes have an up-to-date copy of the data object? So Quorum protocol is going to use voting to figure out which node has up-to-date data object. So here, the basic ideas of the Quorum protocol is require clients to request and acquire the permissions of multi-service before either reading or writing replicate data items. So this idea seems like just send a request and let the server side decide what they have to do, how to manage, how to balance the work, how to manage the work. So the algorithm behavior during write. So we know there are 2 basic operations in this system, read and write. So here we just talk about, we are going to talk about algorithm behavior during write. So first we consider data store and the data object replicate on end server. So that's the environment. So the rule to update an object, a client must first contact at least half end servers plus 1. So students should remember this. So the client must contact at least half end servers plus 1. So it's very important to remember this. And the server gets them to agree to do the update. Excuse me. Once they have agreed, like the server side, the node side agreed, the object is changed and the new version number is associated with the object. So here we are going to use the version technology. So the version number is used to identify the version of the object, and it's the same for all newly updated objects. So the version can help us to find out which one is the new updated items, because we update some information into the data, into the file, and this file have a new version number, like version 2. And the version 1 file contains the old content. So here it's easy to figure out which one is the new update data, and we just extract the version 2, version 1 or version 2, the new version, to get the new updated information. So the algorithm behavior during read. So to read a replicate data object, a client must also contact at least half end server plus 1. So still, this is one important requirement for the system. And ask them to send the version numbers associated with the object. So if all versions number agree, this must be the most recent version based on an attempt to update only the remaining server would fail because they are not enough of them. So I can give you an example. So like we have 2 nodes. So the system only have 2 nodes, node 1 and node 2. So the node 1 contains the version 0 and node 2 contains version 1. And the system, the distributed data store system, is going to read data from both these files, this node. And to get the node 1 just say I have the version 0, and node C I have version 1. So the system will choose the version 1 because it has a higher version number. It means that the version 1 is the new updated data. So the system just sends the version 1 items, version 1 information into the customer because that's what the system have, because that's the new version. So there's no conflict about the version problem, about the update information, update process. So here this is the definition of the Quorum protocol. So N means the number of nodes that store replicas of the data store. So N means the node in the distributed file system, distributed data storage system. So there's an N node in it. And NW means the number of replicas that need to acknowledge the receipt of the update before the update complete. So we can give a very easy definition for this. NW means the number of write node. So that's very easy to understand. So NR means the number of replicas that contact when a data object is accessed through a read operation. So NR can be the number of read node. So yeah, we just give this a brief definition for this NR and W, and so it's easy to understand, to remember. So here is two constraints. If you watch the video, you already know there are two constraints here. So first constraint, NW plus NR larger than N. So that constraint prevent read-write conflicts. And the second constraint, NW larger than N over 2. This constraint prevents write-write conflicts. So here, when you think about these two things, you will think, okay, these are two math equations here. If we combine them together, I get a further constraint that NR larger than N over 2. But this is our assumption. That's our further consideration about these two constraints. So here, I just send this question here. Does this further constraint correct or incorrect? So this is we have to keep this question, this part, in our mind, and we are going to use some examples to prove it. So make sure to prove whether it's right or it's wrong. Because without any samples, we just get these two constraints, and we can that's just the two equations there. And we don't know what will happen if we apply another constraint here, because follow these constraints, it can fit into these two equations. But we have to keep in mind, does that correct? Okay, so let's go to our samples. So I will give you 3 samples. So first one, we don't need, so I will just talk it directly and won't let you do some writing work. So here we have a setup. So in this system, we have 5 nodes. So we have the node 1, node A, node B, node C, node D, and node E. So 5 machines in this system. So the number of writes should be 3, and number R should be 3. So there's no conflict, there's no trouble, the issue about these two constraints. This setup follows the constraints, two constraints. So it means there's no issue or no question about that. So then we are going to do these 3 steps. So first, the server is going to read data from machine A, B, C, and C. Then the server is going to write something on the file of the machine and update this file into machine C, machine D, and machine E. At the last step, the server wants to read the data from machine A, machine B, and machine C. Still, this is the same data for these 3 steps. So let's go to see the graphic of this part. So here, this is our system. We have 5 nodes, 5 machines in it. And for the step 1, we just, the server just read files from machine A, B, C. So first, these 5 machines only contains version 0. So there's no other versions. And the machine A, machine B, machine C send the version 0 file into the read to the server by reading it, by the server send a read request. So there's no question about this read step. So then the server just wants to write something on that file and update it into the machine C, D, E. So here, new version will update to the machine C, D, E. So it means this file have the new versions, version 1, version 1, version 1. So when we stop here, so when we finish read and write part, for this system, only A and the B machine contains the old version 0, and the machine C, D, E contains the new version 1. So the last step, so the system want to read data, same data from this 5 nodes and choose 3 of them. So the system is going to choose A, B, and C machines. So this A will send the version 1 to the system. B will send the version A will send the version 0 to system. B will send the version 0 to system, and C will send the version 1 to system. So compare about these 3 versions, 2 versions, and okay, 2 versions, and the system find there's a higher version number here, the version 1. So it seems like he found the new version among these 3 machines, and the system is going to output the version 1 file to the customer, and the customer can read the new version. So let's go back to our step. Let's go to the next next example, example 2. So here, we have environment, we set up this environment. So still we have 5 nodes here, but we have a different number about NW and NR. So number of write nodes should be 3 and number of read nodes should be 2. So do you think this is a correct setup? So if you have any ideas, you can post on the chat so we can start discussion about this one. So free to share your ideas about this setup environment. So if you have any questions, you can think about these 2 constraints. So the first constraint shows that the number of read. So let's go back to our constraints here. So the first one, see number of write node plus number of read node should be larger than the total number of node. So let's go back to our setup. We find if we plus these 2 numbers, that's equal to the total node of this system, equal to 5. So it's not follow this setup doesn't follow the constraint, first constraint. So it means there must be some issue about the system. But we just keep using this system to find what will happen if we keep using this number of write node and this number of read node. So here, there are 3 steps here. So still there's one customer, and the customer is going to send the read and write request. So first, the server will try to select 2 nodes and read the information from these 2 nodes. So he just select the node A and node B. So then server is trying to update information on the 3 nodes. We just follow this setup. Number of write nodes should be 3 and number of read nodes should be 2. So the server is going to update the information in 3 nodes, C, D, and E. So what will happen if just the server choose A and C and read the data from that 2 nodes? What will happen if we just do the step 3? So can someone just post your answer on it, and everyone can discuss it? I give you 1 minute to think about this problem. So you can take out a paper and draw some graphic and think about what will happen if we do the step 3 on this setup. Also, you can think about if the system just read the information from machine A and machine B, what will happen if we do this step? So 1 minute, just to show your answers or share your ideas on the chat, and I think everyone can start to discuss about that one. So, okay, seems like, yeah, so I can continue to show the, okay, for step 3, if any other node have right. Okay. So let's show you the graphic. How does this work? Right now we have 5 machines. Just a sample, 5 machines. That's a very small dispute file storage system. So we have 5 machines, A, B, C, D, E, and each file contains the old version, the version 0 in it. So for step 1, we just read from A and B. The server just read data from A and B, and the server get version 0 there. So there's no question about the version part. So the server will send version 0 to the customer. But for step 2, the server is going to update information on machine C, D, E. So updated information to the CDE. So here, this arrow says the update. So when the server side do the update work, so the new version number is generated for that file, and the file should be the new version and should be the new one. So for the file in this machine C, D, and E, so they have the version 1. So there's no question about that. So at that moment, so the system contains 2 versions. So A and B contains the version 0, and C and D and E contains the version 1. So the last step, so step 3. So what will happen if the machine read data from A and C? So see the blue arrow. If the machine choose A and C, read data from these 2 machines. So first, machine A will show you the version 0, and machine C will give the version 1 to the server. Then server find, okay, the machine C gives the version 1 which is the higher version than the version 0. So it means version 1 is the new update data, and it will send the version 1 to the customer. So there's another choice. So it means for this first step 3, there's no correction because we get the new version 1 to the customer, and this is the real version, new version 1, real new version in the entire system. So there's no correction. But if we go to the second step 3, so the server choose A and B to read data. So I use the red arrow to show this process. So here, if just the A will send the version 0 to the server, and the machine B will send the version 0 to the server. So the server just consider about these 2 versions and find, okay, the version 0 is the higher version. So there's no question about the version part. So the server just sent this version 0 to the customer, and customer will see, well, I just updated this file in 1 minute ago, but when I read it, why you still giving me the old version? So right now, at this step, the server side has a version part issue. So the data consistency is not implemented in this system because we cannot give the new version part. So here we are going to have hold on. So go back to our constraints. So here we know follow these 2 constraints that are very important. It can make sure your system work correctly. But we think about the further constraints. So what will happen if we just set these constraints? If one system can have different constraints, have different situation about this one. So it means we get the wrong conclusion. But we are going to find one example to prove it. So here, in your mind, you have to think about the NR should be larger than n over 2 or should not be. So here, I give you example 3. So example 3, I said there's a phi node here, still phi node, and the NR should be 4, and NW should be 4, and NR should be 2. So see, if we apply the further constraints into the this environment, it means there's some issue there. But we haven't proved this further constraints, does it right or not. So here but if the first two constraints are worked perfectly, so this setup satisfies the first constraints. So we just run this, though there's no questions about this setup if we just use the first two constraints. So everyone, can you take out a paper and try to draw something, try to draw these steps in it and to see what will happen if we just follow these steps. And what will happen if we, does the further constraint correct or not? And think about this question. So I give you 3 minutes and think and draw about this one. So first I will explain this setup for you. So here, this machine it's working for different users, different clients. So there are 3 clients to do the work. So client 1, client 2, and client 3. So when client 1 finishes write work, then it will leave the server and the client will get in the server. So there's quite different users there, and there's different steps. So you just draw something in your graphic and show what will happen if we do the step 5 and step 6. And think about the further constraint. Does it right or not? I give you 3 minutes, and you can share your ideas into the chat. So if we finish these 6 steps, think about the further constraints, because I make a mistake about this further constraint in the previous. Sorry guys, the internet is not stable. So here, let's go back to our slides. Okay, so everyone can see these slides there? Okay. It's unstable internet, no idea. So okay, let's go to our graphic. So here, this is a problem graphic. So here we also know it's basic information, find node, and each node has the version 0. So first, the client 1 is going to read from machine A and machine B. So the machine A and machine B will send the version 1 to the server. And then step 2, the server will finish the write process and just write information to the ABCD. So this write arrow can show the new version. I mean, the new version will update these 4 machines. So there's no question about this version part, about this client 1. So then client 1 just finished his work, and client 2 jump into the system. And client 2 just want to read the same data, and server just select A and D randomly, just randomly select the A and D. And because right now A, B, C, D has a new version, so A will send version 1, A will send the version 1 file, D will send the version 1 file to the system, and system will send this version 1 file to the customer. And customer say, okay, I got the version, thank you. So, and the client 2 want to update the information. So he just sent the updated request, and the server randomly select 4 machines, B, C, D, E, to update the information. So the version 2 will update these 4 machines. So right now we can see version A. Oh wait, no. When we finish the write part, for client 2, the machine A will contain the version 1, and the other 4 machines will contain the version 2. So you should know in this system there are 2 versions, and only machine A contains the old version and others contain the new version. So when client 2 finishes his work and the client 3 jump in, but client 3 just do the reading work. And for the step 5, client 3 want to read file, and the server select A and B. So select A and B from the nodes, and the A will send the version 1 and B will send version 2. So system will consider about these 2 versions and think the version 2 is higher than the version 1, and the system will decide to send the version 2 to the customer. So the customer will see the version 2. So there's no question about the version. So, and then the client 3 say, I want to read the file again. And the system randomly select the 2 machines and send to access the files. So D and E will are selected for this request, and the machine D send the version 2 to the server, and the machine E send the version 2 to the server. So at the end, the client 3 just see the version 2. So there's no question about these steps. So let's go back to our list part. So when you know, go back to our setup. So you will see the number of write should be 4 and number read should be 2. And when we do finish this part, only 1 machine in this system contains the older version, and the number of reader node should be 2. So it means even though we select A as our read node, we have to select any other node to read the file. So whatever we select from this 4 node, B, C, D, E 4 node, we will get the new version. So it means from this example, we find our further constraint is wrong, because we see NR should be larger than N over 2. But for this example, it works there. It's working. So it means the further constraint doesn't work. So it means we have to delete this part. So unlikely I make a mistake about this one in the previous discussion, and the class discussed about this one and fixed my issues. So I'm very thank you for that, guys. But go back to our slides. So some student will ask, if the number of read node is 1, so we will get the old version, right? But go back to our setup, we'll see the number of nodes should be 5 and number of write should be 4. If we change the number of read node to 1, so the first constraint then cannot be satisfied. So you cannot change this to 1, change the number of read node to 1. So you have to follow the constraint. So if we just follow these 2 constraints, so I'm going to fix my wrong understanding in previous session. So here, these 2 constraints can make sure the distributed file system balance their read and write work and make sure the data consistency and data availability in the distributed file system. So these 2 constraints are very important to get remembered in your mind. So there are 2 special setups here. So I want to do some explain about these 2 special setup. So first, let's go to the case 1, the setup 1. So we say the number of write should be 1 and number of read node should be n. N means the total number of the node. So why we apply this, setup? Because of the heavy reading request from client. So what does that mean? So from this nr equal to 1 and w equal to n. So let me give an example. So think about the library system. So every day, the thousands of students just will access the library system and read some books from it. So it should be a heavy reading request from client, from students. So how to balance this work? So we just say for the system, the server just select 1 node to send the request, to send the data to select the data from it and send it to the user. So it will have a light task on it. But to make sure every node has new version, we have to do this part. So the number of write nodes should be n. It means if the library wants to update a file, it have to access the old node in the system to make sure the student can read the new version part. Because we just choose node one node to read and then send the information to the customer, to the student. So this is one special case. But it's not a special case. It still follows the 2 constraints here. So yeah, you see, nw plus nr equal larger than n and nw larger than n over 2. Still, it just follow this constraint, 2 constraints. There's no questions, but that's a special case why we choose nr equal to 1 in this system. But there's a very special setup. So we have to pay attention to about this setup too. So the nr, the number of read nodes should be n, and the number of write nodes should be 1. So why we choose this system? Because of the heavy writing request from client. So why we choose this? Because of why we choose this one. So think about the heavy writing request. So make sure we have thousands of nodes in the system, and if one write request sent to the server and server has to access every node and update the information, it takes a lot of time there, right? But if we just choose one node and update the information to update the file to a new version, and when we read it, we just select all node and choose the new version one. So it just balance the read and the write process, and we just reduce the heavy writing request to a lighter one, and make sure the system have the high performance. But here, there's a lot of questions about this setup. So think about this one. So one client just send a request to update a file, just one file, file A. So the server side choose the machine 1 to do this update. And the machine 1 finished this updating, but suddenly machine 1 crashed. So the server had to back up and to restart this machine. But at that time, the server is still running, and the reading requests come to this server, and the server just choose the machine A. Server just choose the machine A or machine 1, whatever. Just choose that machine to send it, or choose another machine, not machine 1 or machine A. Select another machine which has the old version, because the machine who contains the old version is crashed, is down, is there. So the server only can get the old version from other machines. But this crash lead to the version problem. So if we use this setup, you have to think about what will happen if there's a crash. There's a crash problem happening into the server side. Also, so think about our previous session. So, like, can we do other work about this setup too? So can you share some ideas about how can we control this setup to reduce the risk of this setup? Can you share some ideas about that? So I think if we have this work, so I mean, if we have this situation, like we have the heavy writing requests from client, and we want to reduce the risk about the crash, and we want to keep the data consistency. So we have to increase this number, even though it will cost a lot of time, a lot of resources. But if we want to reduce the crash risk or reduce the risk about the data missing, data lost, so you have to redesign this setup. So, but I think this setup too is a good direction for us to think about how to manage, how to balance the read and write work about this distributed file system. So also, so in our world, we still thinking about how to make higher performance about distributed file system, how to reduce the risk of it. So still, this is still future research part about this distributed storage system. So, have any questions about our discussion? So seems like we just get it done. So back to the problem 1. So here, problem 1. So if node C goes down, yeah. So C. So yeah, we cannot get this new version. But so if you know that, how can we reduce this risk? Just increase the write process. So let's go back to the question. So how about for this question, how about we just say NR equal to 5 and NW equal to 5, right? So there, if one machine is crashed, there's no issue about the version part. Every machine gets the new version, right? But we have to reduce the task. We have to reduce the cost. So if we develop a real distributed file system, we have to do more about this part to control the risk, the crash risk. We have to do more. Not only just set up this machine and do some random select work, do some basic read and write part. So there should be a very complicated algorithm in it to make sure there's no, complicated about the version part or about the crash problem. So, but based on our example, we don't think about the crash part. But yeah, it's a good idea to think about if the machine C goes down, what will happen? Yeah, it's a good idea. So for the case, so think about the crash problem. if we just use more node to write, it will have a higher cost. There's no, if we choose all node, there's no difference between single node and distributed system. So I think so for the real system, so should be a caching, or should be a memory, or should be a table to catch the read and write request, to catch the crash problem, to catch some machines situations there, machine status there. So to make sure there's no problem about the data consistency. So, but this, I mean, so this discussion is talking about the Quorum protocol. So we just see how this Quorum protocol works in the distributed data store system. So just to give some samples here, and just to give some simple samples here. So, do we have any questions about this? I mean, Quorum protocol. So because we have just finished the time is over, and I'm going to stop this discussion and update. I'm going to update. Will you post? Yeah. So I'm going to post these slides and these videos into the edX, Open edX, to our edX on the resources tab. So you can find this information on the bottom of the page. Okay. So if there's no questions, I'm going to end this discussion, and thank you for everyone to join this discussion. Okay, bye everyone. So if you have any questions, you can post on the Piazza, and we can help you to solve these issues. Okay, so thank you everyone. Bye.